Hello everyone, welcome to Angel's Classroom. In today's class, we are going to see about common collector configuration. So in this configuration, your base is going to be the input terminal, emitter is the output terminal, and collector is going to be the common terminal for both the input as well as your output. So how we draw this diagram? So first we have to draw the NPN transistor. So in this NPN transistor you have to mention the current direction outward in the emitter terminal. Next to this transistor diagram, so C configuration, so I am grounding that collector terminal to the ground, and third one is I am going to insert the ammeter and voltmeter to my input side as well as my output side. So I have inserted the ammeter and voltmeter. Next thing is I have to mark the polarities for ammeter and voltmeter. So for this ammeter at the outward side, in this terminal the current direction is outward. Okay, as you know that the current direction should always flows from positive to negative. To the left of the ammeter I have marked the positive side, and to the right I have marked the negative side. Similar to that, on your input side, this base current is flowing inward. So I have to mark the ammeter positive to my left hand side and negative towards the right hand side. Next I have to mark the name for voltages. So this input side voltmeter is connected between the base and collector terminal. So I am naming it as VBC. Whereas in your output side, this voltmeter is connected across your emitter and collector terminal. So I am naming it as VEC. So this common collector configuration is used for impedance matching purposes, since it has high input impedance and low output impedance, which is absolutely opposite to that of CE and CB configurations. We are going to see the input characteristics. So to determine this input characteristics, see this diagram, I am going to keep my emitter to collector voltage as a constant value, and I am going to increase my VBC in steps, and I am going to measure my base current. Okay. So in this graph my base current should be marked as microamperes. This input characteristics is quite different from your CB and input characteristics. So the main difference is because of that input voltage. Okay. So here VBC is largely determined by your output voltage VEC. Okay. So VEC is equal to VEB plus VBC. Now I am going to keep VEC as a constant value, and I am going to increase this VBC. So because of that, it causes a reduction in the base emitter voltage, and thus it reduces to IB. Next thing is I am going to calculate my current amplification factor gamma. It is defined as the ratio of change in emitter current to the change in base current. So this is known as current amplification factor, and gamma is equal to delta IE divided by delta IB. Next thing, I am going to calculate output characteristics. This common collector output characteristics is similar to that of common emitter output characteristics. Okay, so here we have three regions. First one is cutoff region, saturation region, and active region. IB should be kept constant, and we have to increase VEC voltage, and correspondingly you have to measure the emitter current. So below IB is equal to 0, you will be having your cutoff region, and this slanting line, to the left of the slanting line you have the saturation region, and in between the saturation and cutoff region you will be having your active region. So for all practical purposes, the output characteristics of common collector is same as that of your emitter configuration. Next thing is I am going to calculate the transistor parameters as like we did in common emitter and common base configuration. First thing, we have to measure the input impedance. So this is defined as the ratio of change in input voltage to the change in input current with the output voltage kept constant. Okay. So here the input voltage is VBC and your base current is IB, and the output voltage is VEC. So now I have formulated this equation HIC is equal to delta BBC divided by delta IB. So at this time my VEC should be kept constant and this value typically ranges of about 750 kilo ohms. Next thing I am going to measure the output admittance. So H is for hybrid parameter, O is output and C is my collector configuration. So this is defined as the ratio of change in output current to the corresponding change in output voltage. So here the output current is IE and output voltage is VEC. So now I have formulated my equation HOC is equal to delta IE divided by delta VEC, and at this time IB should be kept constant. Forward current gain. So this forward current gain can be indicated as H parameter, for that is H, and F is for forward and C is for collector configuration. So this is defined as the ratio of change in output current to the corresponding change in input current. So here the output current is IE and input current is IB. At this time the output voltage should be kept constant. So my output voltage is VEC. So HFC is equal to delta IE divided by delta IB. At that time my VEC is equal to a constant value. Next thing is reverse voltage gain. So this reverse voltage gain is defined as the ratio of change in input voltage to the corresponding change in output voltage. Here input voltage is my VBC and output voltage is VEC. So using this I am going to formulate the value for HRC. So HRC is equal to delta BBC divided by delta BEC. At this time IB should be kept constant. So that's all for today. Thanks for watching.